Hello and welcome to the logic of it all. In this video, we will continue talking about logical arguments. If you remember from the previous video, we said that there are two approaches when we are talking about logical arguments. The first approach, which was covered in the previous video, is where we use the truth table of the premises and the conclusion to verify whether an argument is valid or not. Now, in the second approach that we will cover in this video and the next, we do not create the truth table for our premises and conclusion, and instead we just use their syntax to verify whether an argument is valid or not. Now, the problem with truth table, as you remember from the previous videos, first of all, the positive thing about the truth table approach or the semantics approach is that it's very straightforward. It's the same kind of algorithm applies all the time, no matter what your formulas are and so on. The problem with it is when you have, let's say, 4 variables involved, P, Q, R, and S, let's say. Each one of them can either be true or false. So 2 possibilities for the first variable times 2 possibilities for the second times 2 for the third times 2 for the last variable. So 2 times 2 times 2 times 2, that's 16 possible cases, which means that your truth table will have 16 rows. Now, similarly, if you have 5 variables, then your truth table will end up with 32 rows, and then with 6 variables, 64 rows. And in general, if you have n variables, your truth table will have 2 to the n rows. So the size of your truth table grows exponentially as the number of variables grows. And this means that in real practical examples where you have, I don't know, 15 or 20 variables involved, it's fairly difficult or inefficient, let's say, to actually create or generate the truth table and verify the validity of an argument. Now, as we will see in this video and the next, this second approach, which avoids truth tables altogether and only relies on the syntax of the proposition and whether it's a conjunction or a disjunction or an implication and so on, is able to provide shorter proofs that an argument is true. But it comes at its cost, and the cost here is that it's not going to be as straightforward, and it requires a little bit of creativity in some cases. Now, to say more about this approach, what we are introducing is called a deductive system for propositional logic. And what we do here is we introduce a set of rules on how we can derive new formulas from existing ones, from known formulas. And these rules are called inference rules. As we will see in a minute or so, there are inference rules for each connective. There are usually 2 inference rules. One is called elimination, and then the other one is called an introduction rule. And again, these rules only rely on the syntax of your propositions and not their truth table. And the overall thing, that the proof that we create, is sometimes also called a derivation. So if you see derivation in some textbooks, they're referring to the same thing. Now, more algorithmically, this is how it works. We start by listing all our hypotheses, the things that we know or assume to be true. And then we look at the set of rules of inference that we have and see whether either one of them is applicable. And if it is, then we can extend the set of known facts by the new conclusion. And now we have a larger set of things that we know. And we continue doing this until we are able to reach the conclusion. So if we are able to extend this set of known facts until it includes also the conclusion, then we say that the derivation is complete. Now, the way that it works is that every line in this set that we start by just hypothesis and then add a new line every time, every line is either a hypothesis, a premise, something that we assume to be true, or something that is derived from previously known propositions. Okay? Now, before getting into the formal system and rules of inference and so on, let's do an example just to show you that this is not something, very strange, and this is something that you naturally do. We are just trying to formalize the way that we actually think when we are making these arguments. So let's take a look at this example. We have two known facts, or two things that we assume to be true. Fact A says, if today is Tuesday, then I have 10 meetings, I as the lecturer. Fact B says that today is Tuesday. Okay, so two sentences, two propositions. If today is Tuesday, then I have 10 meetings. And then the second fact, today is Tuesday. Now, without knowing anything about logic, just following, natural language and the meaning of the sentences, if you think about it, what can we infer or derive from these two known facts? Right? We can say that, okay, it follows that if today is Tuesday, and also if today is Tuesday, then I have 10 meetings. It follows that I must have 10 meetings today, right? So this is a logical argument, and you can see that it's a valid argument. But really, we don't need to go through the hustle of creating a truth table and looking at all cases and so on and so forth, right? So we can generalize this into a rule that says, if we have two hypotheses, namely the hypothesis that says, if P then Q, if P is the case, then Q follows. And if you also know that P is actually the case, from these two facts, Q follows. Right? So it doesn't matter what sentences you replace for P and Q here. If you have two hypotheses, one of them says if P then Q. In this case, this is P and this is Q. And also, you know that P is true. From these two things, if P then Q and P, it follows that Q must be true as well, which is down here. Okay? Now, this is an example of a rule of inference. We will see this again in later slides with the name and so on. But the purpose of this slide here is that what we are introducing here is not something magical or something very complicated. It's something that you use in your everyday life when you are reasoning about things that we know and things that follow from them. Okay, so this is our first example of a rule of inference, and we will revisit this later on in this video as well. Now, another way to write this is we say, again, we list our known facts or our assumptions on the left side, and then our conclusion on the right side, and this symbol here in the middle. So the way to understand this is that Q can be deduced, or we can infer Q from the fact that P, and also if P then Q. Now, this is again called a turnstile, the symbol in the middle. It's called a turnstile. And it's a syntactic turnstile because we didn't create a truth table for all of this. Remember, we use double turnstile when it's a semantic consequence, and we use truth tables and so on. So that's the general setting. Now, what we are going to do in the rest of this lecture and the next video is introduce all these rules, something similar to what we introduced here through this example. And then for each one of those rules, we are going to look at some examples as well. Now, let's start with conjunction, or and. Okay? Now, the first rule here, again, look at the horizontal line. What's on the top is our hypothesis separated by comma. There could be only one or more hypotheses involved. And then below the horizontal line is our conclusion. So the way to understand this rule of inference is, if we know P and we also know Q, then we can infer P and Q, which intuitively should be true. If you know that P is true and Q is true, then it follows that P and Q must be true as well. And this is called, the name of this rule is and or conjunction introduction, because we introduced this connective down here, the and, in our new formula that we know to be true. There is another version of this that says, if we know P is true and Q is true, we can infer Q and P. So that's also an and introduction. So there are two versions of and introduction. And just to review the terminology, P and Q are the premises in these two rules, And in the first one, P and Q is the conclusion. In the second one, Q and P is the conclusion. Now, using this rule, let's do an example. So look at the turnstile here. On the left side, we have three premises, P, Q, and R. On the right-hand side, we have a conclusion, which is P and Q and R. And we want to use the rule of inference that we know about and the method that we explained to validate or verify that this formula here, P and Q and R, is actually a consequence of P, Q, and R. So if you remember, we said we start by listing our premises. So 1, P is a premise, Q is also a premise, and R is also a premise. Now, what can we do? If you look at the formula that, let me write it here on the corner. We had, if we know P and we know Q, we can infer P and Q. And this was called AND intro. And then the other version was, if we know P and we know Q, we can infer Q and P. And this is also called AND introduction, right? So this is the only rule of inference that we know at the moment. Now, what can we do? And we have an eye on what we want to achieve at the end. So it's P and R and Q. So I say, okay, if I know P and I know R, I can construct P and R using this rule here, right? So I say I can infer P and R, and in front of it, I write my reasoning. I say, okay, this follows from line number 1 and line number 3 because we know P is true, and we also know R is true. And then AND introduction tells me if you know two things, you can combine them with an AND. So I can infer P and R from line 1 and 3 using AND introduction. So this is a new fact that is added to the 3 facts that we had as our hypothesis. Okay, now I know P and R on line 4. I also know Q is true from my premise. So again, I can combine them using AND introduction to get P and R and Q. So this time I used line number 4. That tells me P and R is true. And also line number 2 that tells me Q is true. So P and R and Q follows from line number 2, line number 4, and introduction. So, and then the argument is complete because we have our conclusion in the set of statements that we know to be true. So we start with our hypothesis and then try to infer new statements using what we know above and the rules of inference that we are learning one by one today. And our argument is complete whenever we have our conclusion listed in the list of facts that are known. Now, remember I told you for each connective there is an introduction rule and elimination rule. So now let's talk about AND elimination. So again, there are 2 versions of AND elimination. The first one says, if we know P and Q, remember the top is our premise. Here we have only one premise because there is no comma. So P and Q is the only premise. It says if you know P and Q, you can infer P. Again, that makes sense. If you know P and Q to be true, P has to be true. And the other version is if you know P and Q, you can infer Q. You can infer the second proposition. And that also called AND elimination. So from P and Q, we can infer P. We can also infer Q. Here's an example. So the example says, show that from P and Q, we can infer Q and P. So first step, we list our hypothesis. In this case, we have only one, P and Q. Now, somehow I need to use the rules that I know to get to the right-hand side, Q and P. So first I need to decompose P and Q. So I use AND elimination to get P from P and Q. So from line number 1, by using AND elimination, from P and Q, I can get P. By using the same kind of AND elimination, I can get the second component as well. So I can get Q as well from 1, again, by AND elimination. So I decompose P and Q into P and Q separately. And now I can put them back together using AND introduction, but in the order that I want, which is Q and P. So from line number 2 and line number 3, using AND introduction, I can create Q and P, which is what I was after. So again, that's a proof that assuming P and Q, you can prove Q and P, or Q and P is a consequence of P and Q. Again, you see that there is no need for creating a truth table and then considering all cases, none of that. It's independent from the semantics and only relies on the syntax, on the structure of the formulas, and or, and so on. Okay, now let's move on to the next rule. This rule is called arrow elimination. So it's for elimination of implication, if then. Okay, what does the rule say? This is the one that we did with an example that if today is Tuesday, then I have 10 meetings a couple of slides before. So this should be familiar. It says, if you know if P then Q, and you also know P, from those two facts follows Q, which is, intuitively should be obvious. And this is such an old rule that has a name. So this goes way beyond modern mathematical logic. Another name for it is modus ponens. So sometimes instead of saying arrow elimination, we call this modus ponens. And there is another version of this. So this is called forward modus ponens, when you assume P implies Q and you assume P, and from those two assumptions follows Q. The backward version of it, it says if you know if P then Q and you also know not Q, then it follows that not P. Okay, so that's called backward arrow elimination. We will see these rules used in this example now. Okay, so what do we have here? We have an argument that we want to validate, we want to show whether it's true or not, and it has three hypotheses or premises. The first one is P, the second one is if P then Q, and then the third one is if Q then R. So these are my premises, and my conclusion is simply R. So I want to show that R can be inferred from these three formulas. So again, same algorithm. We start by listing our premises. So the first premise is P, second premise is P implies Q, and then Q implies R. Now, my goal is to reach to R. Now, when you're doing this, it's better to have all the rules, all the rules of inference in front of you to see which one applies. But if you remember from the previous slide, we can apply modus ponens using these two known facts. Fact number 2 says if P then Q. Fact number 1 says P. So from these two, using arrow elimination, we can infer Q. So using line number 1 and line number 2 with arrow elimination, we get a new fact, which is Q. Now, following a similar logic, using Q and if Q then R. So we know if Q then R, we also know Q. Again, using the same rule, arrow elimination or modus ponens, we can infer R. So using line number 3 and line number 4 and the inference rule of arrow elimination, we get R, which is what we wanted to begin with. And that's the end of our proof. So using arrow elimination twice, we can infer R from those three premises. Here's another example of an inference rule. It's called negation elimination. So it says, if you know not P, then you can infer P. So, for example, if you say, it's not the case that today is not Tuesday, then it means that today must be Tuesday, right? Again, this is a rule that is not universally accepted. In classical mathematics, it is accepted, which is the majority of mathematicians and logicians, but there are some schools of thought, like intuitionistic logic, where they don't agree with this rule. But as I said, for classical mathematics, this is accepted by everyone. So that's your premise, not P, and then from that follows P. So here's an example. Again, we have two premises. P is one of my premises, and this thing is my second one. So hypothesis 1, hypothesis 2. And then my conclusion is Q. So again, I start by listing my premises, premise number 1 and 2. And then if you look at 1 and 2, one says if P then not Q, and second one says P. So by using arrow elimination, we can get not Q. So from line number 1 and 2 using arrow elimination. Now what we want is Q. What we have is not Q, which is a perfect place to use the negation elimination. So from row number 3 and using this rule, we can get Q, which is the conclusion that we were after. So that's the end of this proof.